Okay, let's take a look at simplifying radicals lesson 1. And for the first 9 problems, we're just going to simplify these radicals, and of course we're not going to use decimals on this. So we're going to try to break these down into prime factorization and then look for groups of numbers to remove out of the radical. So for the first one, we're going to start with our square root of 18. Remember, if I do not have an index right here, I know that that hiding number is a 2. It is a normal square root. So let's start by breaking down 18 into prime factors. Two numbers that multiply to 18. Remember, you can pick any two numbers that multiply to 18 as long as they are whole numbers and you don't use the number 1 because that's really not doing much for us. So here I could pick like 2 times 9 or 3 times 6. I think I'm going to go with 2 times 9 just because it doesn't really matter. And then I like to, since I'm looking for prime factors, circle my prime number so that I know that I'm done with that branch of the tree. The 9 can be factored even further. Two numbers that multiply to give me 9 is 3 times 3. 3 are both prime numbers, so I know now that at the bottom of every single one of my branches of my tree, I have a circled number, so I have exhausted my list. And what I like to do next is rewrite this problem. I know it started with a 5 on the outside. And then instead of writing the square root of 18, I'm going to write what its prime factors are. So 2 times 3 times 3. Remember, this version of the radicand, this is the exact same number. 2 times 3 times 3 is the exact same as 18. It's just written nicer because now I can see, okay, well, I'm looking for a square root. So that means I'm just looking for two numbers, two of the same numbers multiplied together. So that gives me a perfect square. The square root of 3 squared is 3, so I could take that out front, and that means that I have on the outside 3 times 5, so 15, and this guy is now gone, so on the inside I have root 2. Remember, I am looking for groups of 2 of a kind, because my index is 2 in this case, so if I have 2 of a kind, I can take it out in the front. My answer to number 1 is 15 root 2. Let's try the next one. All right, this time we're going to be looking for groups of 4 prime factors at the same time. If you have 4 of a kind, you can take one of them out of the radical symbol. So before we can do any of that, we got to find our prime factors. So let's reduce this. 80 can be rewritten as 8 times 10, for example. 10 can go to 2 times 5, and both of those are prime. 8 can be written as 4 times 2. 2 is prime, so I like to circle it, and 4 can be written as 2 times 2. Now I have every single branch ends with a circle, so I have a list of prime factors. If I rewrite the problem, it started with a negative out front. I have an index of 4. And then I've got 1, 2, 3, 4 2s and a 5. Remember, the index is the gatekeeper. It tells us we need groups of 4. 1, 2, 3, 4. And if you have a group of 4, you can remove one of them out front of your radical. The 5 is a loner. He cannot come out. He does not have a group of 4. So I'm going to leave that 5 alone inside the 4th root symbol. On the outside, if I make that look nicer, I have negative 2. My answer here is negative 2 times the 4th root of 5. Number 3 should be doable in your head, but if you are stuck here and need to see a visual, you can see it. 49 could be written as 7 times 7, and x squared can be written as x times x. Therefore, I have the square root of 7 times x times x. My index is not there, which means it is a hiding 2. This is a square root problem. I've got a group of 2 here, so a 7 can come out front. A group of 2 here, so an x can come out front. Nothing is left over inside the radical, so that means I don't need a radical in my answer, and my answer is just 7x. All right, let's break down 72. Two numbers that multiply to 72 are 8 and 9. And then I can keep going with the 8 as 4 times 2 and the 4 as 2 times 2. I notice that not all of the bottoms of my branches are circled, so that means I need to go back up to the 9 and keep going. Two numbers that multiply to 9 are 3 times 3, and those are both prime. So if I rewrite this problem, I already started with a 4 out front, just from given in the problem. I'm taking the third root, or cubed root. I've got 3 2's and 2 3's as my prime factorization. Remember that my index tells me the group or the size of the numbers that I need. I need to get 3 of a kind. I've got 3 of a kind, which remember is the same as 2 to the third. Well, the cubed root of 2 to the third, these are inverse operations, so they cancel. So this group comes out, the answer is just 2. Since there is not a group of 3 here, we can't use that inverse operation idea, so these guys are stuck inside. To simplify and write my final answer, I'm going to multiply things back together. Out front, I've got 2 times 4, so that gives me an 8 out front. Inside the cubed root, I've got 3 times 3, so that gives me a 9. So my answer to number 4 is 8 times the cubed root of 9. And for number 5, let's break this down into its prime factors. Two numbers that multiply to 27 are 9 times 3. And two numbers that multiply to 9 are 3 times 3. So that means my listed numbers here are 5 times the root of 3 times 3 times 3. My index is a hiding 2, so I'm looking for 2 of a kind to be able to take out front. I have a group of 2 3's, so I can take that out, and out front it looks like I have 15 times the square root of this guy is my leftover 3 on the inside. 15 root 3 for number 5. Number 6 is another square root problem. Let's reduce 24. I see that as 12 times 2, although there's a lot of ways you could break that down. 12 I see as 6 times 2. Again, you could do it a different way. And 6 is 3 times 2. And finally, I've got all my pairs, or all my prime numbers listed. If I rewrite this problem, it started with a -7, and instead of saying 24, I'm going to say 2 times 2 times 2 times 3, just listing all these guys out. And I know my hiding index is a 2, so I need groups of 2 or pairs of numbers. I have a pair right here. The square root of 2 squared is 2, so that can come out. And these guys are not pairs, so they're stuck inside. If I multiply these numbers back together, on the outside I have -14, and then on the inside of the square root I have 6. So my answer to number 6 is -14 times the square root of 6. For number 7, we need to break down 32 into its list of prime numbers, and then we'll look for groups of 3 to remove from this cube root. 32 is the same as 4 times 8. 4 is the same as 2 times 2. 8 is the same as 4 times 2. And 4 is the same as 2 times 2. Lots of 2's. I like to rewrite so I stay organized. I started with a 10 on the outside, and I'm taking a cube root, and it looks like I have 1, 2, 3, 4, 5 2's in there. There they are. My index says that I need groups of 3 to be able to remove a number. So I have, here's a group, 3 2's, so I can take 1 2 out. And then since these guys can't come out, they are multiplied back together and they stay on the inside. And on the outside, I have 20 when I multiply back together. So my answer for 7 is 20 times the cube root of 4. For number 8, breaking down 24, I see that as 12 times 2, although you could do many different options as well. 12 can be broken down into 6 times 2, and 6 can be broken down into 3 times 2. Now if I rewrite to stay organized, I started with a -6 out front. I'm taking a cube root. I've got 3 2's and a 1 3. My index says I need groups of 3, so I've got 1 right here. Since I have a group, I'm allowed to take one of them out as an answer. This guy cannot come out because he's not a group of 3, so he will stay inside of the cubed root. on the outside, I'm multiplying these back together. So 2 times -6 is -12. So my answer to number 8 is -12 times the cubed root of 3. And then finally for this set, number 9. This one looks scary because it's big, but it has a bunch of zeros in it. So a very easy way to do this is to say this is 100 times 18. And then 100 quickly could go to 10 times 10, and 10 can go to 5 times 2. And there's some prime numbers really quickly. And then we just have to break down 18. I'm going to do 9 times 2, and then 9 breaks down to 3 times 3. So we do have a lot of numbers, so let's keep them organized. I'm going to list my 2's first. 1, 2, 3. And then I've got my 3's next, 2 3's and 2 5's. If you're worried that you didn't get this right, you could check this by typing this huge long number, this radicand, into your calculator. 2 times 2 times 2 times 3 times 3 times 5 times 5, and hopefully you get 1,800. Now, we're not done yet. We still have to look for groups. This is a normal old square root, so I'm looking for pairs or 2 of a kinds. I've got 1, he can come out. I've got another one, so a 3 can come out. And I've got a 5, a pair of 5, so a 5 can come out. So left over, the only thing left inside of there is that singleton 2. And then on the outside, I just have to multiply this together. 5 times 3 gives me 15. 15 times 2 gives me 30. So I think my answer is 30 times the square root of 2. If you're not sure and you want to check, type this into your calculator, get the decimal version, and see if it is the same as the decimal version of this number. Although I don't want decimal answers for this, you could still use decimals to check to see if you have the reduced correct radical. All right, let's move on to multiplication. We know that if you have the same index, you are allowed to multiply and combine the numbers into one big radical symbol. So I think all of these have the same or close to the same index, so we should be able to combine them. Number 10, for example, they are both normal old square roots. Remember, if you do not see an index here, the hiding number is a 2. So this is the exact same type of root, so we are allowed to multiply these together. What I like to do is just flat out multiply them together. So 22 times 8, let me make sure I'm doing this right and double check with my calculator. 22 times 8 gets me 176. So I still have to keep those inside the radical. I have 176. Now I don't want to put that for my answer quite yet because I think I could break that down. So just like above, numbers 1 through 9, I'm going to ask, okay, what 2 numbers multiply to give me 176? Don't think too hard. You literally just use 2 numbers to multiply to 176. So let's use these. 2 numbers that multiply to 176 are 22 times 8. We just used them. And then we can break this down pretty quick. 22 is the same as 2 times 11, and those are both prime. And 8 is 4 times 2, and 4 is 2 times 2. Now if I rewrite this, I've got 4 2's and an 11 inside of that root. It is just a plain old square root. The index is 2, so I am looking for groups of 2. Here's 1, here's another. This 11 is a loner stuck inside, and if I multiply those back together, I've got 4 root 11 for my answer for number 10. That's a similar process to all of these, so number 11 is very similar. Let's go ahead and multiply number 11 together. I've got 12 times 18. Again, I'm allowed to multiply these together because they are both cubed roots. So that will leave me with the cubed root of 216, excuse me, which I could break down. 2 numbers that multiply to 216 are 12 and 18. We just used those. 12 breaks down to 3 times 4, and 4 breaks down to 2 times 2. 18 breaks down to 9 times 2, and 9 breaks down to 3 times 3. If I were to rewrite this, I would have the cubed root of, let's see, 3 2's, and 3 3s. Oh, nice. I say nice because I noticed that I have a cubed root, so I need groups of 3. Here's a group of 3. Here's a group of 3. I have nobody left on the inside of that radical, so that means I don't need the radical anymore, and my answer, I multiply those back together, is just plain old 6. All right, let's try that for number 12 as well. I have both fourth roots, so I'm allowed to multiply these together. I've got 27 times 6, which will get me the fourth root of 162 is what this problem is really asking me for. Again, 27 times 6 gets me 162. I still need to take the fourth root of that, so I'll break it down. Two numbers I've multiplied to 162 are 27 and 6. 6 can be broken down to 3 times 2, and 27 could be broken down into 9 times 3, which 9 can go to 3 times 3. All right, now that I have a list, I could rewrite this as the fourth root of, I've got 4 3s and a 2, and I'm looking for groups of 4. Here's a group of 4 3s, so I can take one of them out. This 2 is stuck inside because he is not a part of a group. So my answer then for number 12 is 3 times the fourth root of 2. Don't forget to include your index in the answer. If you don't have that little index, then I'll assume you're meaning a square root, and that is not the same thing as a fourth root, so be really careful there. Okay, let's try number 13. I've got a plain old square root and a plain old square root. Oh, but now I have numbers on the outside as well. Just like before, we're going to multiply like terms. So this guy, which I would consider like a coefficient, a number out front, is the exact same as this number out front. They are the same kind of number, so you are allowed to multiply them. A whole number 5 times a whole number -2. So my new out front number is going to be 5 times -2, or -10. And then my inside number, I have the square root of 3 times the square root of 7, so that gives me the square root of 21 if I combine with multiplication. My next step here would be to see if I could break down 21. However, the only two numbers that multiply to give me 21 are 3 times 7. Those are both prime, so I would have this as my final list. There are no pairs of numbers here, so I couldn't take anybody out of the radical. So that means that I can't reduce this at all, which means that this must be my final answer. I already have a reduced final answer here as -10 times the square root of 21. Similarly, for number 14, I am allowed to multiply these guys together because they are both fourth roots. So that means I would have the fourth root of 32 times 16. 32 times 16 is 512. So then I will need to break down 512 and look for groups of 4. Two numbers that multiply to give me 512 are the two numbers we just used, 32 times 16. 16 is the same as 4 times 4, which is the same as 2 times 2 times 2 times 2. All of them are prime. 32 could be broken down into 8 times 4. Oh my gosh, here's some more 2's. And then 8 could be broken down into 2 times 4. Oh my gosh, there are so many 2's going on. I'm really glad that I circled them to keep them all organized. Let's organize even further. I'm going to take the fourth root of all of these 2's, and if I count them up, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh boy. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm looking for groups the size of my index, so that case, size of 4. I've got 1, 2, 3, 4 right there, so I know at least 1, 2 can come out. I have 1, 2, 3, 4 right there, so another 2 could come out. And then I've got this loner inside, so a fourth root 2 will be left over, and on the outside 2 times 2 gives me 4. My answer to 14 is 4 times the fourth root of 2. Wowza. Number 15, if I multiply the outside numbers, think about what is the outside number out here. It's a hiding -1, I believe. So I've got -1 times 3, so I've got -3 on the outside. And then on the inside, they're both square roots, so I'm allowed to multiply the 15 times 5 to get 75 on the inside. Of course, now I need to break this down. I know that 15 times 5 is 75, so I could break this down into its prime factorization tree as shown. I've got -3 then times 5 times 5 times 3. It is a normal square root, so I'm looking for groups of 2. I've got 2 5s, so that means that on the outside I have 5 times -3 or -15 times the square root of that leftover loner 3 on the inside. That means my answer to number 15 is -15 root 3. Next up is number 16. And let's think about what my number on the outside is going to be. I have a 3 as a coefficient here, and there's nothing here. So there's technically like a hiding 1. I have 1 of these numbers over here. So out front, I have 3 times 1 or 3, and then I need to take the cubed root of 9 and 36 and multiply together. 9 times 36 is 324. I know it sounds like a big number, but it's not a big deal because we already know 2 numbers that multiply to it. We just used them, 9 times 36. If I break this down further, I have 3 times 3, and 36 can be written as 9 times 4. 4 is 2 times 2 in disguise, and 9 is 3 times 3 in disguise. All right, so that really means I've got a 3 out front, and then I've got the cubed root of 4 3s and 2 2s. My index is telling me I need groups of 3. So since I have 1 here, I can take one of these numbers out. And then I don't have any more 3 of a kinds inside. So on the outside, I've got 3 times 3, so that's 9. And then I've got the cubed root of the leftovers on the inside. Let's multiply these back together. 3 times 2 is 6, times 2 again is 12. So on the inside for number 16, I've got, well, for my full answer, I've got 9 times the cubed root of 12. And 17. Ooh, this one is an interesting one. Be super careful here. I see some numbers in my way. Let me scoot them out. Just clear some room here. Okay. I see that I've got a normal old square root. The index here is a hiding 2, right? I've got a square root, and then I've got a cubed root. That means I am not allowed to multiply these together. Do not type into your calculator 25 times 81 on this problem because you're only allowed to do that if you have the same index. So instead, we're going to have to keep these guys separate for now until we can reduce them enough to be able to combine like terms. Right now, there are no like terms. So let's look at the left side. Well, this is really a very easy problem disguised. Don't get scared about this. What's the square root of 25? You've known that since like 6th grade. This is just a 5, right? The square root of 25 is 5. Now I need to times that by the third root of 81. And I don't know the third root of 81 off the top of my head, perhaps, so we would just break this down. 81 is the same as 9 times 9, and 9 is the same as 3 times 3. So that means that this piece could be rewritten as the cubed root of 3 times itself 4 times. And since I'm looking for a cubed root, I'm allowed to take out groups of 3 for my answer. So that means, so far on the right-hand side, I've got 3 times the cubed root of 3. And now, if I bring down that 5, I've got a 5, and I'm multiplying that. Let's see now if we have any like terms. I have a plain old 5 and a plain old 3, nothing special about them. So I do think I could multiply those with multiplication, or combine those with multiplication. So on the outside, I now have a 15, and then I would just tack this on at the end, 3 root 3, just like I would if I had like a variable. Like if I was taking 5 times 3x, I could combine that together to give me 15x. I can multiply those together and just bring the x along for the ride. So my answer for number 17 is 15 times the cubed root of 3. And finally, the last one for this page is similar to number 17. Number 18, I've got the square root of 50 times the cubed root of 8. We cannot combine these together as is, but let's see if we can simplify and find some like terms. The cubed root of 8 you may already know, but if you don't see it, let's break it down. I've got 4 times 2, and 4 is the same as 2 times 2. So that means I have the cubed root of 2 times 2 times 2. Well, I'm looking for a group of 3. I got a group of 3. I don't have anybody left over, so I think the cubed root of 8, this is just 2 in disguised. Now I have to multiply that by the square root of 50. So it looks like my answer is going to be something like that. However, I think I could break down 50. 50 is the same as 25 times 2, and 25 is the same as 5 times 5. So that means I could rewrite this problem as 2 times the square root of 5 times 5 times 2. This is a square root because there's no index, so I assume it is a 2. That means I'm looking for groups of 2. Since I have a pair of 5s, the square root of 5 squared is 5. On the outside, I now have a 10. On the inside, I have a leftover 2. So my answer for number 18 is 10 root 2. On the back side, we are doing a very similar rule with division. Division and multiplication are very similar in that we need like indexes. If we have the same index, you can combine two different radicals together to form one giant radical. You can also go the opposite way. You can go from here backwards and separate them if you know the square root at the top or the bottom. So basically, we have a bunch of ideas. We could reduce these with division and then try to reduce using the index, or we could reduce using the index and then try to reduce the final answers using division. Let's jump in and see our different strategies at work. Number 9, there are a couple different ways you could solve this problem. One thing that jumps out at me at the very beginning is this is just asking what is the square root of 100, and I know what that is. That's one of those problems that I've memorized from a long time ago. The square root of 100 is just 10, and the square root of 4 is 2. So both of these numbers are easy numbers in disguise. Again, the square root of 100 is 10, the square root of 4 is 2, so I think this problem is really just 10 divided by 2 in disguise, which is 5. The answer to this problem is just 5. Number 20, I do have like indexes, so I am allowed to combine these together. What I mean by that is I could just say that this is the same thing as the cubed root of 48 divided by 6. And you're thinking, well, why do we need to know that? Well, now that these are together, we could reduce these fractions and make them simpler. So think about it. What number goes into both 48 and into 6? Well, I think 48 is divisible by 6. So I could just divide both the top and the bottom by 6 itself. And that means that I have the cubed root of really just 8. 48 divided by 6 is just 8. Now I would break this down and see that this is 4 times 2, which is the same as 2 times 2. So that means I've got the cubed root of 2 times 2 times 2. I'm looking for a group of 3. I have a group of 3. The cubed root of 8 is just 2. So the answer to number 20 is 2. Number 21, can we reduce? If I put these guys together in one giant square root, I've got 18 divided by 2. Well, what is 18 divided by 2? That's just 9. All we've done so far is divide. We haven't square rooted yet. So make sure now you analyze this. What is the square root of 9? It's 3. All right, let's try 22. I'm going to use the rule in an opposite way for number 22. 22 is already written as one giant radical, and I'm actually going to split it up and see if I can solve the individual ones by themselves. The reason why I'm deciding to do that is because I don't think 18 is divisible by 225, so it's not going to really help me make these numbers smaller. Instead, I'm going to write this number as the square root of 18 over the square root of 225. And I'm going to see if I can reduce these separately. I have a hunch that I know the square root of this number, but I'm not quite positive. Okay, let's break this down. 225 is the same thing as, well, what's 225 divided by 5? 45. So 45 times 5. 45 is the same as 5 times 9. And 9 is the same as 3 times 3. So if I'm just focusing on the bottom here, I could rewrite this as 2 5s and 2 3s. I'm looking for a normal old square root, so that means I'm taking 2 out at a time. So this gives me a 5 on the outside, this gives me a 3 on the outside, so that means all together I think I have 3 times 5 on the outside and nothing left over on the inside, so the square root of 225 is just plain old 15. I knew it. This bottom number just reduced straight over to 15. Now all I need to do is reduce the top, the square root of 18. Well, maybe I'll do that up here a little bit. Square root of 18. Two numbers that multiply to 18 are 9 times 2. Two numbers that multiply to 9 are 3 times 3. So that means the square root of 18 could be written as 3 times 3 times 2. I'm looking for a square root, so I need pairs. I can take out that one pair of 3's. So I have a 3 on the outside and a root 2 left over on the inside. I just simply reduce these two problems separately and put them back as fraction form for my answer. So my final answer, when I reduced the top, I got 3 root 2, and when I reduced the bottom, I got 15. Now, I don't really think this is my total final answer, because look here, look at what I just noticed. This number and this number, they're plain old numbers. This 3 and this 15 are just plain old numbers. Could I reduce this any further? Is there a number that goes into 3 and into 15? Well, yeah, I could divide both the top and the bottom by 3, and that means on top I would just have root 2, or if you want, a 1 root 2. And on the bottom, if I divide both the top and the bottom by 3, that means I'd have a 5. So I'd say my final answer to this, completely reduced as far as I could, is the square root of 2 over 5. Again, I got rid of those just by reducing the constant, the normal old whole numbers in the front. All right, let's try this one. These ones are separated, and I think that they will be beneficial if we put them together. I've got 120 over 10, all under one giant square root. And the reason why I did that is because, guys, what's 120 divided by 10? Well, it's just 12. So this is really just the square root of 12 in disguise. And then I could break this down very quickly, 3 times 4 and 2 times 2. So that means I need to know what the square root of 2 times 2 times 3 is. Well, I've got a squared right there, so I think my final answer here is just 2 root 3. 24. Let's see if we could break down just the top. I wouldn't want to put this whole thing into a square root because this is not a square rooted number. I'm just square rooting 200. So let's work with the top really quick. I've got the square root of 200, which I would say is the same as 2 times 100. And 100 is the same as 10 times 10, which breaks down to 5 times 2. So that means that I have the square root of 1, 2, 3 2's and 2 5's. So I'm looking for a square root, so that means pairs. I could take out 1, 2. I could take out 1, 5. So on the front, I've got 10. And on the inside, I've got this 2. Remember, that was just the top. I still have divide by 5 in my answer. I'm tempted to put this on the answer line as my final answer. However, I noticed that both the 10 and the 5 are just plain old numbers out here. These are coefficients or whole numbers. They are not square rooted, so they are like terms. If I wanted to reduce those, well, I could divide both the top and the bottom by 5. This would cancel, and 10 divided by 5 gives me a 2 out front. So I think my final reduced answer is 2 from here, root 2, and the 5 canceled with the 10. Okay, so for number 25 and 26, these are actual problems that we're going to skip for today because you will learn how to do these types of problems. They have a special trick to them, and you will learn how to do them on our next lesson. So you can leave these ones blank or cross them out. Sorry about that, number 26 and 25. But 27 is a totally doable problem. So let's try to break this down. I think we should combine these and try to see if we can reduce this at all. I have this hunch, because these numbers are pretty big, that we could maybe make them smaller before we have to start breaking them down with the factor tree. So what I'm going to do is I use the division rule. Since these are both square roots, I'm allowed to put them under one giant square root. And then what I'd like to do is just to see, well, are these divisible right now? And I just typed it into my calculator. What is 256 divided by 32? And I lucked out, and my hunch was right. It is just plain old 8. This number is just 8. So that means that this question is really just asking, what is the square root of 8? So if I broke down 8, I know that 8 is the same as 4 times 2, and 4 is the same as 2 times 2. So that means I've got 3 2s. I only need 2 of them because my index is a 2. I can take out 1. So my answer here is 2 times the square root of 2.